Okay. So this afternoon's class will be revision of some of the content we covered last semester. And we start with the concept of sets. What can you tell me about sets?
So a set is a collection of items that share some similar characteristic.
Set is a collection of items that share some similar characteristics.
Collection of elements.
Elements, they contain elements. What I want to get at, and at this level, it should be something, it should be apparent. Can we really define what a set is?
It's just want to ask that because the textbook that we were supposed to read, it had that you can't actually define a set. So I was just about to come in here with that.
Same.
Yeah,
I was
it said well
because
defined.
I didn't want to be wrong.
Because
Right.
here that a set is a collection of objects, right? But do you see the issue with trying to define what a set is?
Yeah, it's kind of like we'll keep running into stuff that we'll need to keep defining.
Yeah. You see
We
that
can
it's-
never get like a definite definition for it.
Mhm. So you start by saying, if you may, that a set is a collection of objects. What do you mean in the mathematical sense of a collection? What exactly is a collection? And when you define the word collection, there may be a word in there that may require you to define as well. And then in that definition, may require you to define another word. And you keep on defining words and you never reach to a point where all words are properly defined. And in mathematics, remember, it's the study of all well-defined concepts. So we refer to sets as a primitive concept. It's a primitive concept. And any primitive concept in mathematics is a building block. They do not require definition, but they are used to define other things. And anywhere you start, you always have to have building blocks that are going to be used as the fundamentals, and they're going to be used to define other concepts, right? So when we start talking about a function, for example, we don't just talk about a function is a rule just like that. Function must be something that is defined on sets. If you do not have sets, you cannot have a function, right? So the basis for functions, sets. Same with relations. You want to define a relation, you must have sets. Without sets, you cannot define relations. But sets can stand by themselves without needing any other thing to define. Now, so we have to come to this level at university to know that we can't really define a set. Then why is it all along that we keep on learning and we keep on teaching as well that a set is a collection of items that we call elements? It's just to help us understand, right? So any definition we give is really done for understanding. But in higher mathematics, you don't speak of it as a collection. People who use it in daily life don't go in the details as mathematicians do. And so it suffices to use objects, right? So we can write that here as in an attempt to try to to help us understand what a set is. It is a collection of objects called, I guess, not just any collection, but a well-defined, right? Well-defined. And what this well-defined part means is that you must know for certain whether an element is in the set or not in the set. A well-defined collection of objects. The objects, as we know, are called elements. And if an element is in a set, we write it as that way. The common letter is the element and the capital letter is the set. And if it is not, we say that it is not in this. The element is not in this. All right. Now, there are two ways in which we can specify the elements of a set.
Yes, sir. We can use a characterizing property, or you can list the elements.
That's correct. We can list the elements, and that is called the set roster notation, right? It's where you list the elements. Or we can use the characterization property, and that one is called the set builder notation. Characterization property simply means pick something that you want to be common among all the elements. Look for all of those elements that have characteristic, group them together, and you have a set. So we want to put cars into a set. We can use a color as a characterization property. We can pick red, and all cars that are red, we put them together. That is the characteristic, right? And we end up with a set. So when we're listing the elements, we can write it as A is equal to 1, 2, 3, 4. It can be a finite set, but we can also list it in terms of an infinite set. 1, 2, 3, all the way to positive infinity. And in terms of the set builder notation, on the other hand, we can say A is equal to the set of all X such that X is an element of the positive integers and X is less than or equal to 4. And this notation is the set builder equivalent to that notation. All X such that X must be a positive integer that is less than or equal to 4. Positive integers start from 1. So you're counting 1, 2, 3, 4. It means that this X will take on the value 1, 2, 3, 4. And we say less than or equal to 4. So 4 is where we're going to stop. Any questions so far?
No, sir, I'm okay.
No, sir.
Right, let's move on. I have some space here. I can maximize it. If one set is contained in another set, okay, if set A is contained in set B, then we can write that as A, this symbol B. And this symbol is the subset notation. right? That's a subset.
Question, sir.
Go ahead.
I saw that in the textbook they were using it in the reverse. So they had like B and the subset symbol in the reverse and then A. Is that read the same way or it's read differently?
Okay, so it depends on how this thing is written, right? So let me show you some ways in which it can be written, and it means the same thing. We can have B contains, the set B contains A. And so reading this, it means that A is inside of B.
Yes.
Which is inside has the closed end of the symbol. And the one that has the open side is the larger one. And in this
So
notation,
kind of like inequality
Yeah.
sign. Okay.
It's just like inequality. That's right. This one here is called the subset. And this one here is called the superset. The larger of the two is the superset, and the smaller is the subset. But just to clarify, can you tell me the way the textbook worded it so that we know what it's saying?
I can't remember them giving a like worded. All right, let me
I
go
believe
back
it's
to
the same thing here, you know. I believe it's the same thing. They utilize this symbol here for
No,
A.
I mean, when they have it out in Word and then they're going to write it symbolically, I want to know how what did they,
Yeah, that's the thing. They didn't write it out in Word. So the definition state that a set B is a subset of set A denoted
Okay.
by B subset of A. Or they have A
And they
is
reverse the symbol.
subset symbol, but they reverse it in the other direction.
Yeah.
So I just want to know, like in worded version, how do I say that? Because I know that if the first one you have in blue, I read that as A is a subset of B. But if they have it as B, the subset symbol being open to B and A, how do I read that? Like if I'm explaining it to you or doing a presentation, how do I say that in words?
Okay, so
Do I
you're
say
saying
B contains
I
A
have
or yeah, that's what I was.
that, well, not that way. I think I know. It's B, and you have it like that.
Yes.
That?
Yes.
Yeah, so you can read it as A is a subset of B,
Okay, okay. So you just read.
right?
Okay.
Because look, if I have 5 is greater than 2, 2 is less than 5, I can read this as 5 is greater than 2. Well, I can also read this one as 5 is greater than 2.
Yeah, that's true. So it's
Okay.
read the same way in essence.
Same way.
Okay.
Always remember, the closed end is always the smaller one, and that one is going to be called the subset. So again, this one here is the subset. And this one here is the superset. Okay. Now we know that every set is a subset of itself, right?
Yes.
Do you know what name is given to that?
The improper subset.
Very good. Improper. Improper subset. It's a set. A set is a subset of. So you say that the set is a proper subset of itself, and then all other subsets are the proper subsets. Okay, so if we have A is equal to 1, 2, 3, we say that A is an improper subset of A. Okay, A is an improper subset of A. But if we have another set that is B equal to 1, 2, then B is a proper subset of because B contains B does not contain all of the elements that are in A. And that is why sometimes you're going to see the symbol this being used or that being used. Now we have to be careful with when we use these symbols and what we mean, because some people believe that once they see the symbol, that the sets are automatically equal to each other. Now, if I have X is less than or equal to Y, does this mean that X is necessarily equal to Y?
No.
It could be less than or
Or
equal to Y. So in the same way, when you have A is a subset of B, this means that either A has less elements than B has, or A has the same number of elements as B has. So it could be a proper or an improper subset of B. But when you use this notation, if you use this notation, you're saying that A is a proper subset. Because A will definitely, the elements of A will definitely be less than the elements of B. Is that clear, Divina?
Oh, yeah, yes, sir. Sorry.
Maya, are you following so far?
Yes, sir.
Great. Let's continue. Can anybody tell me what power set? What is a power set?
sorry, the power set of A will consist of all the subsets of A.
Correct.
Yes.
Correct. A power set is a set which contains all subsets of another set. Right? So the subsets of A would be 1,
And we have 2.
3, 1, 2, 1, 3, 2, 3, 1, 2, 3, and one more. What's that other one?
The empty set.
Right. And the formula is if A has n elements, that's how you write it. You read it as the cardinality of A, right? Cardinality, we'll talk about this shortly. Cardinality means the number of elements in the set, right? Number of elements in the set. So if set A contains n elements, then the power set of A contains 2 to the n elements. Okay? The set A has 3 elements, and so 2 to the third is equal to 8. Power set contains 8 elements. Okay? Now we talk about cardinality of a set. And we know that the cardinality is the number of elements in the set. For example, if set A is equal to 1, 1, 2, 3, then the cardinality of A is equal to
2.
3.
3. How did I miss that one?
Right? It's equal to and not 4. Because I want you to think of it, right? In terms of now when we're going to move on to do a mapping. And we have an element, we have the elements 1, 2, 3 here. And then we have some other elements over here, A and B. Let's say that 1 maps onto A and then 1 maps onto B, we do not put another 1 here and map it onto B, do we?
No, you just draw an arrow from 1.
If we do that, will we ever have anything such as a many-to-one relation or a many-to-many relation? We wouldn't. Think about it. If every time you see a number, you write it as a unique number, it means that you will always have 1 arrow leaving here to go over. So you will never have 2 arrows leaving one thing because you're treating this one as a different element from this one. But it is the same element. So be careful when you're dealing with cardinalities.
So should we say that the cardinality is a number of distinct elements in a set?
That is the operative word. It is the number, not just any element, it's the number of distinct elements of the set. Okay. If we want to say that set A has the same cardinality as set B, we need to show that every element from every unique element in set A maps onto a unique element from set B. Okay, so if A is equal to alpha, beta, gamma, and B is equal to A, B, C. The cardinality of A is equal to the cardinality of B because we can write the elements of A as alpha, beta, gamma, and the elements of B as A, B, C. And we can show that whenever somebody picks an element from A, that it maps onto a unique element in B, and no set has any extra element that has not been mapped. This works well for finite sets. But when we have infinite sets, the story is a bit different, right? Because when we have infinite sets, we cannot show that one element maps onto another element for all possible elements. So what we might have to do in that case is come up with a function. You know, we haven't talked about function yet, but we have to come up with a function that will guarantee us, without us listing all elements over here and mapping it with all elements over there. Go ahead, Jack.
So what about finite sets that are really large? Can we also use that function? Or is there another function for large finite sets?
Well, so the thing is, right? Infinite sets usually have names to them, and we know what their elements are going to look like. It is possible that you have a really large finite set that contains element like and, hash, ampersand, right? And you remember a function is going to take one element from this set here and map it onto an element in another set here. So the question is, how is it that you're going to be able to define a function? And remember, a function has to be a general rule that can take something from here and map it onto something in another set if there is no pattern, or because how do you take, for example, this symbol and multiply it by 2?
Right.
Right? The only, and so we know that when we're dealing with numbers, that in those cases, it's possible to have infinite sets because numbers are the only thing that are truly infinite. We know for certain that numbers go all the way to infinity, and therefore functions can allow us to come up with a general rule that map one element onto the other without us having to specifically check them one by one, right? So let me give you an example, but before we do, let's talk about, we'll come back to cardinality. we'll talk about a bit more about it and how interesting discussion. We'll have an interesting discussion with, but so some common sets are, we have the set of Z. This is the set of all integers, right? So this set is negative, well, from negative infinity, -3, -2, -1, 0, 1, 2, 3, all the way to positive infinity. We have the set Q of rational numbers, and this is all numbers of the form P divided by Q, where P and Q are integers themselves, and Q must not be equal to 0. That denominator is not 0. We have the set R of real numbers. Real numbers. And then we have the set R complement, which is the set of, well, I probably should use Q and Q complement, right? Q and Q complement. This is going to be the set of irrational numbers. Then we have the set C of complex numbers, right? And then we can take Z and put a plus above it.
Positive integers.
And what's the set of positive integers also called?
Oh,
Whole number?
Say that again.
No, whole numbers that contain 0. I don't know. I think in
natural numbers.
Yeah, there's
Natural.
it.
So Z, the set Z plus is natural numbers, right?
And we can have Z star.
All right, and I'm just about to talk about that. What does the star mean now when you see that? The star tells, anybody knows?
Yes, sir, we omit 0. We omit 0.
All numbers except 0 that
Yeah.
can possibly be in this set. So we go from negative infinity to -3, -2, -1, skip 0, go to 1, 2, 3, so on and so forth. Right? So you can have Z star, you can have Q star, and basically the star tells us that it is a set that does not contain 0. This is going to be useful because some of the structures that we will look at, for example, a group, the axioms that you have to check, usually it holds for all members except 0. And so rather than discarding the whole set because it doesn't hold for one element, but it holds for every other element, you just take 0 out of it. And so one of those properties that I'm talking about is the inverse property, and specifically the multiplicative inverse, right? Sure, Jackie. Specifically the multiplicative inverse, 0, whereas for the number 5, its multiplicative inverse is 1/5. For 0, it doesn't have a multiplicative inverse. So we usually end up with problems, and that is why we talk about the set of non-zero elements. We just take out 0 from these sets, right? So we have those sets there. Now coming back to cardinality, we can actually show that the set Z has the same cardinality, same number of elements as the set of Z plus. Although the Z contains all of these numbers and the Z plus starts from here. And you may think that, okay, Z plus is a proper subset of Z, and it is, which means that it doesn't have all the same elements that Z contains, but yet we can say that it has the same number of elements as Z. And if we can get a function to be certain that every time somebody picks a number from Z, it's mapped onto an element from Z plus, then we can determine that these two sets have the same cardinality. So if we list the members of Z plus, right, we'll have 1, 2, 3, 4, 5, 6, 7, and we go on. And then we're going to map 0 from Z to 1. We have a 1-to-1 correspondence there. Then 2, we'll put to 1. Then 3, we'll put to -1. 4, we'll put to 2. 5, we'll put to -2. And if you notice, what we're doing is that from Z, we're dividing it into the set of even numbers and the set of odd numbers. Whereas for Z, we're dividing it into the set of positive integers and the set of negative integers. And what we're doing is assigning even numbers from Z plus to positive numbers. So 2 is mapped onto 1, 4 is mapped onto 2, 6 will be mapped onto 3. And you notice that it is actually twice as much. So you know for certain that if somebody calls the number in Z, which is 1000, the corresponding number in Z plus that maps onto it, notice the relationship. Z plus is at the bottom and Z is at the top. The Z value is twice as much as the Z plus value, right? No, this one is Z plus at the top and this one is Z at the bottom, right? And we see that the Z plus value is twice the Z value. So the number 2000 is be mapped onto 1000. And we're taking the odd positive integers and map them onto the negative integers. So we see that 3, for example, goes to -1, but we can even, and then we have a special case for so here. But what I can do, let me change it around like this. Let me put it as -1, 1, -2, 2, -3, +3. So I'm just switching. I'm now saying that the odd numbers are mapped onto the positive numbers and the even numbers are mapped onto the negative numbers, and it will be the same thing. And then we have a special rule again for we're mapping 1 onto 0 because 0 is neither negative nor positive. So we'll have to split this set into positive, negative, and 0 and have a special rule for 0. And so we can come up with a function that allows us to do this. It's actually going to be a piecewise function, right? And so that piecewise function will generally tell us that any value you put in, I probably should put n here, any value you put in for Z plus will give you the corresponding value for Z. Okay, so if we, for example, enter 1, we want 1 to give us 0. So we can probably say that this here is equal to 2 times n minus 1. So let's see, when we put 1 into this thing, 2 times 1 is 2. Maybe not 2n, that will just we can use minus n plus 1 divided by 2 if n is odd. And you know why? Because when n is odd and you add 1 to it, it becomes even. And when you divide an even number by 2, you'll have a whole number, which is what integers actually are. So let's see, let's pick an odd number. Let's pick the number 3, for example. So we have 3 plus 1 is 4. 4 divided by 2 is equal to 2. Okay? And so we can then use this function to remap these things. No, in fact, let me leave it as it is and just make a change to the function itself. Let me put in this thing here. Let me put in here a minus 1 like that. So let's see if it works. When n is equal to 3, 3 minus 1 is 2. 2 divided by 2 is equal to, let me see if it works for 5. 5 minus 1 is equal to 4. 4 divided by 2 is equal to 2. Gives me exactly that. And remember, previously what I had was the 2 was mapped onto the positive and the 3 was mapped onto the negative. To accommodate for that, you just put the negative sign in front here. And you can see it, right? Now, so we're okay with the having all of the odd, having all of these numbers here, right?
Yes.
1, 2, and 3. How do we get now the negative 2 and negative 3? And that will happen if n is even. We'll have to put a negative, of course, in front to accommodate the negative signs.
Would it be negative n over 2?
Right. And then we have divided by 2. Okay, we have n divided by 2. And so let's see if this works now. When n is equal to 2, minus 2 divided by 2 is minus 1. When n is equal to 6, minus 6 divided by 2 is minus 3. So all of these are accounted for. Let's see if the 0 is also accounted for. Notice that n1 goes to 0. So that tells me that n is odd, right? N is odd. So when I put a 1 here, 1 minus 1, 0 divided by 2 is 0. So it accounts for that as well. So what we have done is come up with a function that generalizes this pattern that we're seeing. And it tells us that for any z plus you pick, you have a corresponding z. And that will confirm that, once we can show that this function satisfies injective and surjective, then it means that these two sets have the same cardinal. Okay. And of course, these are not written as definite. It depends on how you want to assign your mapping. Like I said, if you're going to have here this as positive and that as negative, you swap the sign in this piece. Okay. On the other hand, oh, and by the way, infinite sets that have the same cardinality as the set of natural numbers fall into a group of infinity that we call Aleph null. That's kind of like a symbol for it. Aleph null, A-L-E-P-H, null, and it is the smallest level of infinity. There are infinities that are larger than the Aleph null infinity. And the set of real numbers has a cardinality which is larger than the cardinality of the set of natural numbers. In fact, if we say that x is a real number such that x is between 0 and 1, this subset of real numbers has a greater cardinality than the set of natural numbers. We cannot find a bijection that will map the two sets, a function that can map the two sets. What are you seeing right now? My screen? You're still seeing my screen?
Yes, sir. We're still seeing the blackboard.
Because it has frozen a bit, so I was wondering. I want to show you why it is that using a demonstration, why the set of natural numbers and the set of real numbers have different cardinals. Give me 1 second. Okay. This little diagram will help us understand why the set of natural number has a different cardinality from the set of real numbers. Now remember, in order to ascertain that the two sets have the same cardinality, we are looking for a function that will map every single element from one set, which is of natural numbers in this case, to the elements of the other set, which is the real numbers in this other case, in such a way that we're certain that no ends gets left out. Now assume that we have all real numbers possible like this, and we have a mapping from the set of natural numbers, 1 all the way to positive infinity, to all possible real numbers as we see them here. If we can come up with a real number and justify that that real number is nowhere in this list, then it means that we have a real number that has not been mapped onto anything, where all of the other numbers or all of the real natural numbers have been mapped onto the other real numbers. So if we can pick out one that we're sure is not mapped onto anything and justify why it is not mapped onto anything, then we have a good case. And this is how it is. So remember, we're saying that we have a function that will map the natural number 1 to this decimal number here, to this real number, which is the number 0.4, but we're just putting a set of zeros behind. Then the number 2 is mapped onto 8.5, the number 3 to 7.505, like that. Now, we're going to construct a new real number that we will call B. Or let's use R for real number, right? We construct a new real number that we call R. And the procedure is as follows. We put 0 point, right? You want it to be a number between 0 and 1. It doesn't, so we start off with 0 point. Now where this first decimal point is for this first number, that's a 4 there, right? So because it's a 4, we're going to replace it, we're going to put a 0. We don't want it to be the same thing. We move down the diagonal and we come to the second number in the second row. There is a 0 here. Where there is a 0, you replace it with a 1.
Mhm.
So where there is a 0, you replace it with a 1. And where there is not a 0, you replace it with a 0. Okay? So the second one, there's a 0 here, we put a 1. The third number, this is a 5, we're going to put a 0. This is a 0, we're going to put a 1. This is the 6, we're going to put a 0. This is a 5, we're going to put a 0. This is a 5, we're also going to put a 0. This is a 0, we're going to put a 1. This is an 8, we'll put a 0 there, and it goes on like that. And it is guaranteed that this number that we constructed is nowhere on this list where we have one-to-one mapping between all possible natural numbers and supposedly all possible real numbers. And here is why. Clearly, right, this number cannot be the same as this first number because the decimal place is off. We made it that way. That decimal place is off. It cannot be the same as the second number because the second, even if this and that were the same, the second decimal place would have been off. It cannot be the same as the third number because even if this number here, even this R starts off at 7.50, we constructed it in such a way that the third number in the third row is different from what is given there. And so, do you think this number will match up to any of these numbers on this list?
No, sir, no. It will never be matched to one of the natural numbers. It will never be matched.
And therefore, this is going to be a new real number that is not on our list. New real number, not in the list. And that tells us that we have more real numbers than natural numbers. Okay? Divina, are you following?
Yes, sir, I'm following.
Roseanne, any question?
No, sir.
Maya, any question? Okay. Let's talk about functions. Or before we talk about functions, let's talk about the Cartesian product, right? Cartesian product. If we have two sets, A and B, the Cartesian product is written as A cross B, right? And it's actually the set of all ordered pairs of the form AB such that A is an element of set A and B is an element of set B. We know this, right? That's what the Cartesian product is. So if we have A is equal to 1, 2, 3, and B is equal to AB, then the Cartesian product of A and B is equal to ordered pair 1 goes with A, 2 goes with A, and 3 goes with A. Then 1 goes with B, 2 goes with B, and 3 goes with B. Visually, this here is set A with elements 1, 2, 3. This here is set B with elements A, B. And the Cartesian product maps every element in the first set to every element in the second set. That's what the Cartesian. Okay. From the Cartesian product, we can get a subset. And does anybody know what that subset is called? A subset of A cross B is a what?
Subset of A cross B.
Meaning that, so right now we see that there are 6 arrows. 6 arrows leaving set A and going to set B. If we take a subset of those arrows, so not considering all 6 of them, but maybe 4 out of the 6 or 3 out of the 6, that's a subset. What do we get?
Would that be a relation?
That's good. A relation. That's why I left that space there. It's called a relation. And a subset of A cross B satisfying certain conditions is a function. So any subset is a relation, but only those subsets that satisfy a special property or special condition is called a function. Right? Which brings us to functions.
Sir, sorry, but can you just go back for just 1 second, please?
Sure.
Thank you. Yes, sir. Can continue.
Functions. Okay. So look at this. We take set A with elements 1, 2, 3, and set B with elements A, B, and we're gonna find a Cartesian product, A cross B. Sorry. Okay, and that to that, this to this to that, and this to that. That's the Cartesian product, right? And what we're gonna do is to take out this second arrow going there, or in fact, take out everything. And out of those 6 arrows, we will choose only a specific subset of arrows to draw. And those specific, let's draw from 1 to A, let's draw from 2 to B, and let's also draw from 3 to B. Now this subset of the 6 arrows, we only pick out these 3. This is called a function. And that special condition that we talked about just now is actually the condition that when you look in this set here, you must have a single arrow, leaving every element. That is what makes it a function. If two arrows leave the number 1, this is no longer a function. And if we mapped 1 to A and 2 to B, but 3 is not mapped, then it is not a function. That is the special condition. Okay. Mathematically, we define a function as follows. We can say that a function f from A to B. And when we talk about functions, this set A has a special name. It's called the domain. And this set B also has a special name. It's called
Codomain.
the is a mapping such that for all x in A, there exists a y in B such that f of x is equal to 1. Now, when we say for every A in x in A, that is the same as writing this thing out in words. See, a single arrow leaving every element. This every is that thing. That is this point being written mathematically instead of being drawn in a diagram. So for every x in A, there exists a y in B. And notice for this part, it doesn't say that there exists a unique y in B, meaning that every element over here must have their own thing over here. That doesn't have to be the case. All 3 of these could be mapped onto A, or all 3 of them could be mapped onto B, and it will still be a function. The only thing that you need to check for a function is that a single arrow leaves every element in from that every x is mapped. It doesn't matter that all of them are mapped onto the same element. In that case, it will be what we call a many-to-one function. And we know that it's a many-to-one relation, and we know that many-to-one relations are functions. From functions, we can get 2 special type of functions. The first one is called an injective. And what's another name for an injective function?
An injection. I think you wrote it there, sir.
Also called
Is this the one? Yeah.
Okay.
one-to-one. An injective or a one-to-one function f from A to B is a mapping such that for every x and y that are in set A, so for all elements in the domain of A, right? If you put x into the function and you get the same thing as if you put y into the function, then this must mean that x and y are the same element. That is what it means to be a one-to-one function or an injective function. So this is what a function looks like diagrammatically. Let me show you what an injective function looks like diagrammatically. We have A, 1, 2, 3, and we have B, 1 to A, B, C, D. And we have A1 going to A, 2 going to D, 3 going to B. It does not matter that in the codomain something is unmapped. That's totally fine. But nothing must be unmapped over in the domain. So this is a one-to-one function or an injective function. From an injective function, we can move on to talk about a surjective function. What's another name for a surjective function?
Onto.
Onto. Surjective or onto function. F from A to B is a mapping such that I want you to compare what I'm writing. Look at what I'm writing and compare it with the definition of a function and see how they're different. That's what the surjective function is. What seems to be the difference?
For the one-to-one, it's like a unique output. Every input has one unique output.
We're not comparing them, we're comparing source.
Oh, to the function, sorry.
Those two definitions.
So I'm seeing some reversal here, right? From the function definition of function for every x and a. And if you look at the surjective, we're dealing with for every y and b.
Yes.
The definition starts with consideration of the A set. And for the surjective, it considers the B set.
Domain and codomain, right? So remember what we talk about, how it's okay for an element over here to be mapped. A surjective function means that it is not. A, B, 1, 2, 3, A, B. That goes to that, this goes to that, this goes to this. This is a surjective function because all elements in set B are 1. And another way that we can write that a function is surjective is like this. Anybody read me in words?
Oh, okay. So I think this is the range of f is equal to b.
Now what is B?
B is a codomain.
Yes. The function is surjective if the range of the function is equal to the codomain. Okay. Let's take 10 minutes break. And when we return, we'll finish up with functions. Because remember, this is just a review. This is not our interest, our main interest in this course. This was the main interest in the previous course. So we'll continue with our review of functions, and then we will get into a bit of relations and equivalence. 10 minutes, okay?
Yes, sir.
Right. I'm going to draw a diagram now on this board, and you'll tell me what specifically about functions we will be discussing. But before we do, let me talk about something else very importantly. We know that if a function is both injective and surjective, then it is referred to as a what type of function? Does anybody know?
If
Function
it's both
is
injective and surjective,
Right.
bijective.
Yes,
It's a bijective
it's
function.
called a bijective function. And a bijective function is both a one-to-one function, and remember one-to-one is injective, right? And an onto function, which is surjective. And bijective functions are the only function whose inverses are also functions. If a function is not a bijective function, and you take the inverse of that function, that inverse will not be a function. Okay? If the function is bijective, and you take the inverse of it, the function, then that inverse will also be a function. Because look at what's going to happen, right? Let us say that, let's look at this function here. This function is a one-to-one function, but it is not surjective or onto because the element C is mapped. When you're dealing with inverse functions, you are switching the domain and the codomain. So now if the arrows are changing directions, it would be required that an arrow leave every single element over here instead, but no arrow will be leaving C. Because what we'll be doing when we take the inverse function is just take the head of this arrow and put it in the other way around, right? And so because no arrow is coming from anything over here to C, when this becomes our domain and that becomes our codomain, we have an element that is unmapped. And so therefore that violates this condition that a single arrow must leave every element from the domain. On the other hand, if the function is surjective only, as we have it here, and this becomes our domain and that's our codomain, and we switch the arrows around, we have another issue where two arrows will be leaving this element. So we know that when two arrows leave this element, we do not have a function. And so the only type of functions that have inverses are bijective functions. Because you will have, in bijective functions, you always have the same number of elements in this set as over here. And all you're doing is just changing the direction. An arrow is going from and to a single element, and all we're doing is changing its direction. And it will maintain the property of a function. Okay, so I'm going to draw a diagram now. Even before I'm finished, tell me if you know what concept we'll be talking
Transitivity.
about. No.
Oh, there's got to be something with composition of functions.
Yes. This is function. That is function G. And okay, so this is set A, set B, and set C. If we take a point X from set A, we pass it into this function F, it gives us this output point in set B called f of x, or y equal f of x. And then we take this f of x point and pass it into g. It gives us this function here, g of f of x. And let's say that this is a new point, which we call c. A composition of function tells us how we can get from one set to the other without going through a middle set. And this function is going to be g of f. Now, when we write a notation for composition functions, this is the order in which it goes. This is telling me that I am evaluating function f first, followed by function. Okay. And the thing about composition functions is that composition of injective functions is injective. If you take two injective functions and you compose them, the composition will be injective. If you take surjective functions and you compose them, the composition will also be surjective. Which means that if you take bijective functions and you compose them, then the composition will also be bijective. And while a composition of function is not commutative, in that g of f is not the same as f of g, what we can say is that the composition of function is associative. Associative means that you're not moving the terms around, you're only changing brackets. So whatever operations you're working with. And so if we have an associativity, always will work when you have at least three things to talk about. Commutativity will work for two, but associativity and distributivity will work for at least three. You don't talk about associativity when you have two elements. So if we have a composition of function that look like this, f of g of h, and we evaluate g of h first, this is the same as if we had evaluate f of g first, and then we evaluate h. Remember, in associativity, you do not switch the order of the elements. It remains as f of g of h, f of g of h. All that you're changing is the brackets, which tells you which portion of this thing you will be working with first. Okay? And that is a bit of the revision. I just want to talk about briefly. I want to talk about, let's talk about partitions, and then we talk about relations, and then we talk about, well, let's talk about relations first. Relations. Let's just have a brief discussion on relations, and we'll call it. We won't go all three of us. So essentially, this is the definition for a relation, as Divina rightfully said, right? A relation R on a set. You do not necessarily need two different sets. It can be one set. So on a set S is a subset of the Cartesian product between the set and itself. Okay. Something that you're going to come around often is this. We say that the element 3, right? The element 3 is a real number. But we cannot say that the element 3, 4 is a real number. We have to say that it is an element of the real numbers squared. And r squared is really r times r, cross product of r with r. Because now we have two numbers, and two numbers cannot live in a single dimensional space. Each value you put in this bracket represents a dimension. So this real number 3, well, this number 3 lives in that one-dimensional space, which is a line, a single real number line. You put the number 0 there, you put the number 3, and here is where that number lives along this line, along this real number line. When you try to represent the number 3, 4, you can't do so on this one-dimensional line. You can represent 3, but this one-dimensional line only moves back and forth. Whereas 3 and
Need a Cartesian plane.
right, 3 and 4 goes in 2 dimensions. The first number tells you right and left movement, and the second number tells you up and down movement, right? So, and likewise, you're doing multivariate calculus this semester. You talk about functions of 2 or more variables now. So we can substitute 3 and 4, and we can get an output of 5. Then this triple, so each one of these things are called tuples, and this one specifically is a triple, right? This triple resides in 3-dimensional space, R cubed. So you have a height, you have up and down, you have right and left, but you also have front and back, like that. So you think of it, because you see it's difficult to represent it because we're drawing on a board which is 2-dimensional, and I'm trying to represent 3-dimension and 2-dimension. So how you think about this line, which is this green one, as if I'm holding my pencil up to the screen, and it's coming out of the screen and going into the screen. That's the 3rd dimension, right? Why I'm saying that is so that you understand that a relation is a subset of not a set, but the Cartesian product of the set on itself, or between sets, which means that a relation is it's not gonna contain a single number as its element. It's going to contain a pair of values as its element. It's going to have a first value A and a second value B. So when you write A, comma B, this, and we say that A is in relation with B, we really mean that we have an ordered pair AB, where A is the first element and B is the second element. Okay. Suppose we have a set S, and this set contains the elements 1, 2, 3, and we want to define a relation on this set. We want to define a relation on the set S as follows. Let's say the relation is equal to the set of ordered pair XY such that X is greater than Y. That's of course in set roster notation, and we want to list the elements now of this set XY such that X is greater than Y. So to work with this, what it means, right, is this. This first element, goes here, and this second element goes there. And we now have to pick out pairs to put into this relation, into this new set. From, remember we're defining it on S.
Yeah.
So
So
if
you
I,
can look at 2 and 1.
but right, but if I put 1 and 2, is this an element of the relation?
No, it cannot be.
No, sir.
No, because if I put 1 here and 2 there, because remember the order is X, Y, 1 there and 2 there, 1 is not greater than 2. This is not an element of the relation. So what are some things that are going to be elements of this relation?
We have 2, 1,
1,
followed by 3, 2. Yeah, we can put 3, 1 as well. Yes.
1,
Yeah,
anything else? Do we have any other element in this ordered pair?
I cannot think of any right now. I think that's it.
That's our relation. So notice that the set has individual real numbers as its elements. So each element from this set belongs to the set of, it's a real number, right? Or belong to the set. But every element of the relation, none of these, this is an element of the relation, that is an element of the relation, and this is an element of the relation. Our relation has 3 elements, and none of these elements is an element of S. Because each element here comes as a pair, but each element in S is a single number. However, each element here is actually an element of S cross with S, the Cartesian product. Because think about it, what's going to be the Cartesian product? If you write S 2 times, won't S cross S contains the element 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, and 3, 3. Aren't these the elements of this Cartesian product S cross S?
Yes, sir. Yes.
And do you see that from these 9 elements, if we pick out this one, that one, that
Can see the relation. Yeah, the relation is a subset there.
so the relation is a subset of the Cartesian. Okay.
Yes, yes.
Relation is a subset of the Cartesian product. We can talk about 3 important properties of relations.
We have reflexive, reflective, and transitive.
Oh, you remember? Properties of relations. You did this in discrete math, right?
Yes, sir. Plus in the notes from the textbook, they have it there.
Yes.
It's chapter 0.
And so for those of you who are doing discrete maths this semester, this is actually going to be easy for you when we reach the topic of relations. It's basically the same thing, right? So properties of relations. There are 4 actually that we talk about, but only 3 in this course. Reflexive.
Oh, the other one is symmetric. Symmetric.
And the third one is transitive. Okay. You will write a definition for these based on your reading. Let me show you how they work. If I have a set S, and remember, right, I keep on reiterating that relations and functions are all concepts that have set theory as their base. Set theory is a primitive concept and is the foundation. So we cannot talk about a relation without having it being defined on a set or on sets. And it's the same with functions. Okay? Give me 1 second. Pause me all of it. Right. So, like I was saying, we always define these concepts on sets before we can make use of them. So if we have a set containing the elements 1, 2, and 3, okay? And then we would define a relation on the set. We're not going to use a formula. We're just going to pick out some random and put them into this relation. So this is what I'll do. I'll pick out 1, 1 and put it in the relation. I'll pick out 2, 2 and put it in the relation. I'll pick out 3, 1 and put it in the relation. And I'll pick out 2, 3 and put it in the relation. Okay. In order for a relation to be reflexive, you need to look at the set. That's a must. You go back to the set, look at all of its elements, and you have to ensure that each element is paired with itself in the relation. So I'm looking to see that in this relation, I get the element 1, 1, 2, 2, and 3, 3. There is 1, 1, there is 2, 2, but there is no 2. So this relation is not, it is not reflective. If we define another relation, and we have 1, 1, 2, 1, 2, 2, 3, 3, that's it, then this relation is a reflexive relation. Because for all elements, let me write the definition here. For all elements in the set, we must have that the element is in relation with itself, which means that you're expected to see all pairs of the form XX in the relation. So in this set, I'm looking for 1, 1, 2, 2, 3, 3. There is 1, 1, 2, 2, and 3, 3. So therefore, this relation is reflexive. Okay, let's talk about symmetry. We're using the same set S, 1, 2, 3. And we will define, I probably should put subscripts here, R1, R2, R3, third relation defined on the set S to be 1, 2, 2, 1, 3, 2. In order for a relation to be symmetric, so notice now, when we're talking about reflexive, we're saying for all X in S, which means you go to the set, and you look at all of the elements, and you must ensure that they're paired with themselves. That doesn't happen for symmetric. Symmetric is saying if X is in relation with Y, then we expect Y to also be in relation with X. And what that means is that if you see a pair XY in the relation, you must also see a pair YX in the relation. And remember, there is a if there. So this doesn't depend on the set now, this just depends on the relation. Look at the relation. If I see a 1, 2, I must see a 2, 1. You have to flip it. Yes, that happens. But I'm seeing a 3, 2 here, but I'm not seeing any 2, 3. And because of that, this relation is
Not symmetric.
It's not symmetric. I'll go again. R4 equal to 1, 1, 1, 3, 3, 1. Now, again, if looking at the relation, I see a 1, 1. Well, 1, 1 is the flip of itself. I see a 1, 3. And when I flip 1, 3, I get 3, 1. So these two are the inverses of each other, the flip of each other. So because I'm seeing all elements where there's an XY, there is also YX, this relation is symmetric. Okay. Finally, for transitivity, this is saying if X is in a relation with Y and Y is in a relation with Z, then X must be in a relation with Z. Okay, so reflexive deals with one element X. Symmetric deals with two elements X and Y. And transitivity deals with three elements X, Y, and Z. Think you see that?
Yes, sir.
Element, then two elements, transitivity, three elements, right? Is that okay, Rosa? Divina, is that clear?
Sir, following.
Okay. Then finally, we can talk about transitivity. Let's say we have R5 is equal to 1, 2, 2, 3, and 1, 2, 2, 3, and 3, 1, 3. 1, 3. We want to know whether this relation is transitive or not. So what this is telling me is that if I see something of the form XY and YZ, so this second number matches onto this first number, then the first number here and that second number there must be in one bracket. So I'm looking at a 1, 2, and then a 2, 3. I must be able to find a 1, 3, and a 1, 3 is here.
Yes.
Next, I look for a 1, 3, and do I have any that starts with a 3?
No.
No, well, that doesn't work. That doesn't count like that. Let's now start with this one here. If we have a 3, do we have any that starts with a 3? No. So you got to check for each one, right? So that one is out too. But for this first one, we have a 1, 2. Do we have any that starts with a 2? Yes, we have a 2, 3, which means there was a 1, 3, and we do have a 1, 3. So therefore, this relation is a transitive relation. Transitive. One point I must make is that any relation with one element, and you know what you call a relation with one element? Do you know what you call any set with one element?
So a singleton.
That's right. Singleton.
I remember something.
Relation with one element is transitive. And this is proven vacuously. So by default, if you have a relation R6 and it only contains the element 1, 3, you don't need to check anything. So by default, it is going to be transitive. So remember that one. And the reason for that is because there is a big if in front of it here. And what it's saying is that if one thing, you go from 1 to 2, and then you go from 2 to 3, you're supposed to be able to go from 1 to 3 directly. But notice that when we start from 1 to 3, there is no other thing that starts with a 3 for us to jump to. So by default, we don't have to count those. So if we're using that same line of reasoning with this one, this is just a single element. There's nothing that comes after it, so this one doesn't have to be checked. Okay, and when we do discrete graph theory in discrete mathematics, you will understand how you can use a graph to represent these relations here. Essentially, this is what it means. And you can even use a matrix as well, right? So this is how you know whether a relation is reflexive. The leading diagonals are all 1. So let me show you what I mean. What you do, you put a 1, 2, and 3 there. And you put a 1, a 2, and a 3. Now let's say we have a relation, and that relation is 1, 1, 2, 2, 3, 3, and 1, 3. These are the elements of the relation, and we want to represent it using a matrix. 1, 1 is this element of the leading diagonal. This is 2, 2, and that is 3. So if 1, 1 is in the relation, you put a 1 for yes. 2, 2 is in the relation, so you put a 1 for yes. And 3, 3 is in the relation, you put a 1 for yes. Other element that is in the relation is 1, 3. 1 is here, 3 is there, so you put a 1 there. And all other places you fill with 0. Because the leading diagonal contains all 1s. It is this matrix tells us that the relation R is a reflexive relation. And we can use a matrix to also determine whether a relation is symmetric and a relation is transitive. We can, if we don't use a matrix, we can use something that's called a graph. And in a graph, you just have points. This is the point 1. This is the point 2. This is the point 3. So what you do is the things that are related to each other, you connect them by a line. 1 to itself. This is what we call a loop. 2 to itself, another loop. 3 to itself, another loop. And then we have between 1 and 3. And this tells us, this graph tells us that the relation is reflexive. And from a graph, you determine that if each point has a loop means it goes back to itself. So there are different ways of representing this. But of course, in this course, we are not going to go through the different ways of representing it, just so that you know that there are. Okay. I'll stop here for today, and we'll continue tomorrow.